Hi guys, welcome back. Before we get into the world of analog audio and analog audio transmission, I want to talk to you a little bit about sound and what exactly sound is. So sound is the vibration of any object. We hear that vibration through any medium. So the medium that we mostly hear sound is the medium we live in, and that's a gas, that's air. So what happens is when I clap my hands hit molecules. Those molecules hit the one next to them, which hits the one next to that, and hits the one next to that, and so on and so forth. And the molecules from me to your ear continue to vibrate. They vibrate, they move inwards from the source, and they move outwards. And we call this compression and rarefaction. They do this over and over again, forming a wave. Now, if you just have a look at this, I've just drawn a wave over the top of a diagram displaying compression and rarefaction. So if you come to think of sound in a wave, what properties does a wave have? Well, if we look at this, the wave's moving in 2D space on the horizontal and on the vertical. So if we look at this, it moves this way and it moves this way. Now, the density of the wave horizontally, or the frequency, how many peaks and troughs this wave has, will dictate pitch, and we'll call this frequency. The height of the peaks and troughs, so how high the wave is, dictates amplitude or volume. We'll call it amplitude. Just to recap, so frequency is dictated by repetitions of the waveform, and amplitude is dictated by the height, the peaks and troughs of the waveform itself. So what you might notice to begin with is that amplitude is more subject to change over distance. So as a sound loses its power, it loses its amplitude, it becomes less audible. So knowing that amplitude is the height of the peaks and troughs, what would a louder sound look like? Well, let's have a look. So this is the quiet sound. This is the louder sound. So you can see the frequency is unchanged. Now, what would this sound look like if it was lower frequency but the same amplitude? It would be spread out and there'd be less cycles in the waveform. What if it was a higher frequency but the same volume? As you can see, it'd be more dense, there'd be more cycles in the waveform. So I wanted to address two more small points. And this is the way sound behaves when it's added together. Now, this is important because it's at the core of mixing. And this is what we do. We add sounds together and we shape them into a final stereo product, or many mono products if you're doing foldback. So I want to look at what happens when we take one waveform and add it to another. So we've got our original waveform, and it's exactly the same. So the troughs are in the same place. The peaks are in the same place. These are two identical sounds. Add them together, and what happens is you get an increase in amplitude. Sometimes sounds can be out of phase to each other. They are exactly the same sound, same amplitude, same pitch, but the waveform is backwards. Where there is a peak, there is a trough, and where there is a trough, there is a peak. Now, why is this important? Because when you add those two types of sounds together, you get a different result. So this diagram is an example of what happens when you have two sounds that are exactly 180 degrees out of phase and identical to each other, and you add them together. You actually get silence. They cancel each other out. And we'll work a little bit more on phase throughout the semester. Now, the last thing I wanted to touch on is just to make sure you have an accurate picture of how this waveform looks. Now, the waveforms I've been showing you, these are sine waves, they're pure tones. And the sound you're hearing in the real world, the sound of my voice, isn't a pure tone. It's made of many frequencies. This sound here would be one frequency. See how perfect the waveform is? Now the tone, or the pitch of this, would be dictated by how many cycles. So I'd suggest you get a tone generator onto your phone and have a look at what a 1000 hertz or 1 kilohertz sound looks like. Have a listen to a 100 hertz sound, 150 hertz sound, have a listen to a 4 kilohertz sound, so you understand what these are and the frequency point that aligns with what you're hearing. what happens if it's not a pure sound? It's not a sine wave. It's something you're hearing in the real world. It's likely to be a wave on top of a wave on top of a wave. So you might be imagining, well, how does that look? Well, it kind of looks like this. It just complicates the waveform. And so you have your original tone at 80 hertz and another one at 100, another one at 120, 140. You have all these frequencies from everything that's audible, 20 hertz to 20 kilohertz, and they're all riding on top of each other, just creating a far more complex waveform.